My favorite kind of math problem is one that looks simple, but then leads to some interesting stuff. And it's obvious that 2 to the power of 4, 2 times 2 times 2 times 2 is 16, and 4 squared is also 16. But what if I said, I was wondering if there's any other numbers that fit this pattern, where a number to a power is equal to swapping this number to that power. And one of the math teachers in my math department posed that question at the end of a professional development meeting, and we all kind of obsessed over it for a second for a variety of reasons. One is just spotting other solutions. It doesn't seem like there are any other nice integer solutions like 2 and 4, 4 and 2. However, it is pretty obvious that if x and y are the same number, you get other solutions. But what if I wanted to express other solutions? What if I wanted to do algebra and solve to get y by itself? This is kind of a fascinating situation. Also, if you type this into a graphing calculator that can handle things like this, like Desmos, you get a really interesting graph of the solution set. So I was also just curious if by solving it for y, I would get any insight into this graph, which, for example, seems to have an asymptote at 1, meaning it seems to get infinitely close to 1 for the outputs here, and it's completely symmetric. I mean, the symmetry is pretty obvious because if x and y are swapped, you get exactly the same equation. Y to the power of x equals x to the power of y. So some elements of the graph are obvious, but others like the asymptote are less obvious. Also, I suspected that this point was probably EE. Now, do you know what E is? It's an interesting number, comes up a lot. And it does seem like that is the point EE. So can we get any kind of insight into this and what's happening algebraically? And I'll try to keep all the algebra at mostly an Algebra 2 level, high school math. Occasionally, there'll be some very small calculus ideas, and I'll even try to explain everything so that somebody who really has very little idea about algebra even could potentially, with interest, follow this video. We'll see. So anyway, if I'm dealing with exponents, and I want to solve for them, my first thought is I should take the logarithm of both sides. Now, why is that the case? Well, first I'll show you what happens. So I'm going to take the natural logarithm of both sides of this equation. So I am going to use this as an input into a log, and that will still be equal to using this as the input into the same log. Now, if two things are equal, then I can change them both in the same way. I can use them both as inputs into a logarithm, and those two things would stay equal. This is kind of the whole idea behind algebra and why it works. If two things are equal, then those things can remain equal as we change both of them. So I can take this, use it as an input here. I can take this, use it as an input here. And these things are nice and equal still. Cool. Now, the reason I'm doing this, when at first it makes things look worse, is because then we get the exponent to drop down as multiplication in front. Now, this might not at all seem obvious, and you might also be like, what the heck even is a logarithm? So I feel like we're going to take a little side path over here to talk a little bit about logarithms. What the heck is this ln thing I'm doing? Why do exponents get to drop down? And all of that. So we are going to do a little side story about logarithms. So it's possible you've learned about logarithms or not, but really logarithms are just a different way of expressing the idea of an exponent. So for example, if 2 to the power of 3 is 8, meaning 2 times 2 times 2, that's a 2, is 8, we could express the same idea using different notation. I could say the logarithm with a base of 2, so log base 2 of 8, so I'm inputting 8 into a log base 2 function, this would be equal to 3. And I don't know why my 3 has an extra little curl on it here. This is a 3. So what we're saying is that these actually mean the same thing. This and this mean the same thing. This is essentially the definition of a logarithm. A logarithm is an exponent. It's a way of describing an exponent by saying the base number you use the exponent on and the result you get after doing the exponent. So if we express this idea in general, this means that if I have a base number to a certain power and it equals a certain result, maybe b, so a to the power of m equals b, I could say that the logarithm with a base of a of b is equal to m. So this means that a to the power of m is equal to b. So the logarithm base a of b means the exponent that I use on a base of a to get b. And m is the exponent that I use on a base of a to get b. So these are equivalent. That's really all logarithms are. They're just a different way to write down the idea of an exponent by describing the base you use it on and the result. Now, what about this weird thing I'm doing here where I'm writing ln, not log? That just means that the base of the logarithm is e. So if the base of the logarithm is e, we call this the natural log, and we just write ln to mean the base of the logarithm is e. Now, what about this weird thing about the exponent dropping down in front as multiplication? Well, this is also pretty easy to explain. So let's just use some logic here. So let's take a log with no specific number for the base. Let's say m of a, and let's say that there's an exponent on this input into the logarithm. Okay. Now, what we're saying is that I could take this exponent and drop it down in front as multiplication. Now, that would be this, n times log base m of a. And the question is, would these things be equal? And if so, why? So you may have at some point in math memorized that this is a thing, but do you know why it works? Well, it's actually just based on a property of exponents, because remember, logarithms actually just are exponents. That's all they are. They're a different way of writing down exponents. But if I want to prove that these things are equal, I have to maybe think about exponents and what they mean. So the log base m of a to the n actually just is equal to some exponent. So let's call that exponent p. So I could express this idea as p is the exponent I use on a p is the exponent I use on a base of m to get a to the power of n. So p is an exponent that I use on the base of m to get a to the power of n. These have exactly the same meaning. Now, if I wanted to express this side as an exponential, it might give us some insight into whether or not these things would be equal. Well, to express this as an exponent, I could say, okay, I want this whole thing to be equal to q, and then I might try to write it as an exponential again. The problem, though, is that this n is sort of in the way, because now I can't just ignore that and say m to the power of q is a, because this n's kind of in the way. So we're going to do the power of algebra again, which is if two things are equal and you change them in the same way, they remain equal. So we are just going to divide both things by n, and then these two things would, in fact, remain equal. So that means that we now have n divided by n, which is just 1. So we have 1 times log base m of a, and times 1 doesn't do anything. And that's equal to q over n. Okay, so now I should be able to write this as an exponential, because remember, all log means is an exponent. So this just means that the exponent that I use on a base of m to get a is q over n. So that means that if I have a base of m and I use the exponent q over n, that this would be equal to a. Okay, that seems interesting. Now, I'm noticing something. There's an a over here, and there is an a right here. And remember that, well, I can't assume these two things are equal, because that's what I'm trying to prove. I am saying that the a here is the same as the a here, the m here is the same as the m here, the n here is the same as the n here. I'm just wondering, are these two expressions, when they're arranged this way, equal, right? So I do know that this a is the same as this a, which means we can just do substitution. Again, the power of algebras, if two things are equal, they're interchangeable, right? So a is the same thing as m to the power of q over n. So that means I could just put that here. So that would give us something a little bit nicer to look at. This would be m to the power of p equals m to the power of q over n to the power of n. And you might be like, okay, well, what the heck is that? Well, that actually simplifies. Powers of powers multiply. And if I multiply by n and divide by n, I'm essentially doing nothing. So this is just m to the power of q is equal to m to the power of p. But if you're a little bit rusty on your math and you're like, wait, why do powers of powers multiply? We could take a little side trip over here, because this is the whole reason this whole logarithm thing works. This is the power property of logarithms, and it's based on the fact that powers of powers multiply. This is called the power property of exponents. Now, this should actually be fairly simple if you think about it. Like if I have 2 to the power of 3 and I square it, you might be like, okay, what does that mean? Well, 2 to the power of 3 just means 2 times 2 times 2, and if I square it, it just means I multiply it by another copy. That is a 2, by the way, not a 1. Another copy of itself, 2 times 2 times 2, which just means I have 6 copies of 2 in a row multiplying together, and the parentheses are just saying, you know, do this first and do that first. They're a grouping symbol, but everything's just multiplication, and the order of multiplication doesn't matter. So we have what's called the associative property, which means I could just kind of change where the parentheses are or just ignore them. So this is just 2 to the power of 6. And so in general, we would say that if I have some number like x to the power of m, that just means I have m of them in a row, and then to the power of n just means I have this many groups of it. So I have n groups of m things, so that is what multiplication means. That means, why did I write an m there, though? That means that we have x to the power of m times n. So that is all that's happening here. These multiply together, and n over n, or multiply by n divided by n, cancel out. So we have this. Now, what does that mean? Well, if m to this power is equal to m to that power, that can only be true if the exponents themselves are actually equal. So that means that p must be equal to q. Now, why was I doing any of this anyway? It was because I didn't trust that you would happen to remember why the exponents can drop down when I do this. So basically, we just proved that for any values in your logarithm expression, if you have an exponent inside the logarithm, you can drop it down in front as multiplication, and everything's good to go. So that's why I did this. So anyway, I now no longer have exponents, although I do have logarithms, which, you know, are going to be their own thing. I'm also noticing I've got x's and y's on the same, on the same side, but I got y on this side and also a y on this side. I don't like that. I want the x's and y's to be on the same side. So what if I divide this side by y? Well, y divided by y would cancel out, but I've got to do both sides. So now this side is divided by y. And what if I divided this side by x? Well, x divided by x would reduce to 1 and simplify out of the problem, but then I also have to divide the other side by x. So I can essentially take this, and if I was hoping this would move nicely, there we go, divide it over here, and so we end up with this. Well, that's not too bad, except I still don't really have y by itself. I have it on the same side of the equation. So at this point, I'm thinking, is there any way I can make this a little bit more manageable to work with? Well, one thing is I want to focus, like both sides kind of look the same. I just want to focus on the y's right now. So one thing we kind of do in math sometimes is we just say, okay, what if I just said that I'm going to call this whole group the letter K, just so it's easier to look at. So I can just think about that whole side as the letter K. That's going to be easier to look at. And now I'll just focus on this thing over here. So I'm just going to worry about this. Anyway, what were we doing? So I rewrote this as being the same thing as K. So we can just make this side easier to think about, and I don't have to keep writing it down, because we're going to focus on the right-hand side of this equation. And I think it's going to be nice to write this as 1 over y times the natural log of y. Now, why are these the same thing? Remember that division is the same thing as multiplying by the reciprocal. In other words, dividing by y is the same thing as multiplying by 1 over y. Think about specific values. Dividing by 2 is the same thing as multiplying by a half. Dividing by 3 is the same thing as multiplying by a third. Now, the reason why I'm wanting to do this is I think there's a chance to write this as something times the natural log of the same thing, which I think would be easier to work with. But wait a minute, 1 over y and y aren't the same thing. That's true. So I think I can turn this y into 1 over y by, once again, taking the power of algebra. So remember, this side is just k. So I have an equation. Two things are equal, so I can change them in the same way. I'm going to multiply both sides by -1. So this side is just going to now be negative k if I multiply it by -1. Now, I can multiply this sign by -1, and I'm intentionally going to think about the -1 as multiplying this factor, the natural log. Remember, if you multiply three things together, the order is up to you. So I don't really want to worry about changing the 1 over y. I want to multiply a -1 by the natural log of y. And the reason I want to do this is this same log property that we already proved. If I have an exponent inside a log, it can drop down in front as multiplication, but you could also use that in reverse. If you have a number in front of a log, you could bring it back in as a power inside the log. So if two things are equal, right, you can use that either way. So I'm going to take this exponent and I'm going to put it on this y. So that is going to be y to the power of -1. Now, negative exponents just mean to multiply by the reciprocal. So this means 1 over y. And by the way, that should make sense. People sometimes get confused by negative exponents, and why do they mean multiply by the reciprocal? Well, they just mean the opposite of positive exponents. Positive exponents just mean do repeated multiplication. A negative exponent should just mean do repeated division. And so repeatedly dividing by y is just multiplying by 1 over y. Remember, the multiplication by the reciprocal is what division means. So these are the same thing. So this is the whole reason why I'm choosing to do this, is so that I can put that here, which gets me this, and rewrite it as 1 over y. And the reason I wanted to do that is so it matches this thing. So we now have 1 over y times the natural log of 1 over y. And the other side is just negative k, because we had to multiply by a -1 in order to get here. Now, why am I doing this? Okay, the reason why I'm doing this is I wanted these to match, and I'm also kind of hopeful that we can get into a format that I know how to deal with. I know how to deal with things that are of a format where, let's say v equals u times e to the u. Or you could think of this as y equals x e to the x if you prefer using y's for outputs and x's for inputs. We've already defined x and y to be something else over here, so I don't want to like mix those things up. What I'm trying to say is that multiplying a linear factor times an exponential, where the linear factor and the exponential both have the input variable, is a thing that comes up sometimes in math, and there is a way to deal with that. So my strategy right now is trying to get into this format, even though I'm in this format right now. And so my strategy is going to be, well, what if I rewrite this factor as e to the power of something? Now, how can I do that? So there's kind of another trick you do with logs sometimes, which is, the one I'm using right now. So let's explain it. So let me put it like this. If I have e to the power of the natural log of something, let's call it m, it actually should be obvious, if you think about what logarithms mean, that this whole thing is just m. By the way, that's supposed to be an m. Okay. Now, why would these actually be the same thing? Well, there's a lot of ways I could explain it, but I want you to actually just think about what this means. This literally means an exponent. This means the exponent that you use on a base of e, remember natural log has a base of e, to get m. So this literally means this is defined as the number that I use as an exponent on an e in order to have it equal m. And now I'm using that number as an exponent on an e. So I get m. That's literally just the definition of logarithms. So because of that, I can actually take any number I want. This is just something that I can always do. I can take any number I want, and I could put that number inside a natural log, and then I could do e to the power of that natural log, and this is equivalent to the thing we started with, the thing inside. This is just a different version of the same thing, because this just means the exponent that I would use on a base of e to get 1 over y. So I'm using it on a base of e, and I get 1 over y. These are equivalent. Now, you might feel like this is making the problem worse, not better, but remember my goal was to get into a format that looks like this, where I have e to some power times the same thing that as that power. And guys, we just did it. Because remember, this blue part is this, but then we still have the red bit. It would be this whole thing times the natural log of 1 over y. Now, I think this will look nicer if I go ahead and just change the order of multiplication here, where I kind of put this in front like that, because now it's going to look more like what we're seeing here. And then remember, the left-hand side of the equation was negative k, right? We're just tracking that down. So these two things are still equal. Okay, so we have this. Now again, why did I do that? Because that's literally this. If I said that u is the natural log of 1 over y, then I have that in both places. So in fact, I mean, that kind of looks like I just divided by u, so I don't want to do that. So I'm going to say that u is this, but that means it's also this, which means that I can write this entire thing as negative k, that's just the left-hand side, equals, this is just a u, so this is u times e, and this is also just u, e to the u. So I now have something that is in this format, and that means I can actually deal with it. Okay, so how do I deal with these things? So this is going to be its own little exploration. So let's actually get some space, make sure we have enough room to deal with this, and just kind of talk about this for a little bit. So what is this? So this is essentially saying I have a function where I could input u, and it will output v. So we might think about an input-output table. So I input u, and it outputs v. So let's think about what sorts of numbers we would get out of this. So for example, if I input a 0 for u, I would get 0 times something, which is always 0. What would happen if I input a 1? If I input a 1, I would get 1 times e to the first power, which is just e. 1 times e is e. So if I input a 1, it outputs an e. What would happen if I input a negative 1? If I input a negative 1, it would mean that I would get negative 1 times e to the negative 1. Well, negative 1 times e to the negative 1, remember that a negative exponent just means multiply by the reciprocal, so this just means negative 1 times 1 over e, which is just negative 1 over e. So this would be negative 1 over e. So basically, I get a table of values that I could make for this. We could even make a graph if we wanted to. I'm not sure that's strictly necessary here. But let's go ahead and just think about this for a second. Okay, so there is something. Now, there's a fancy name for this, which I don't know if it's even helpful to bring up, but I guess I will. This is called the Lambert W function. And the Lambert W function is literally just saying, what if I just treated this in reverse? What if I do the inverse of this? What if, instead of this being inputs and this being outputs into this function, what if I just took that same idea, but I called this the outputs and I called this the inputs? In other words, I'm just switching what we consider the inputs and the outputs. That's the definition of what an inverse function does. So in that case, we would get these results. The results would be where I input v's and it outputs the u's, and this would be negative 1 over e, and it would output a -1. And if I input a 0, it would still output a 0. And if I input an E, it would still output, a 1. So this is the idea of the Lambert W function. So the basic idea, though, is just that if I input stuff into W, if it follows the reverse process of doing this, what that also then means is that if I input V into W, I get U. In other words, if I input this, I get this. That's the important thing to understand, because what this now lets me do is I can write this as saying, okay, that means that if I take, W as my function here, and I input this, I'm going to do this on both sides. Remember, -k is equal to this, so I'm just inputting that. This goes ahead and just outputs U. That's what it outputs. So I now have U by itself. Now, that's good if we want to solve to get Y by itself. Now, why is that good? Because remember what U actually is. U is the natural log of 1 over Y. So that means that I could now remember that U is the natural log of 1 over Y. I could just say, okay, so let's get Y's going again here. So that is that. So this means that I almost have solved to get Y by itself, except it's still trapped in the log. Now, when that happens, it's going to be useful to cancel out the logarithm. Now, we can use the same trick again that we've used before. E to the power of a natural log cancels out the natural log and just leaves you with the thing inside. Hey, look, I want to get this Y out of being in this natural log, so I'm just going to raise this to the power of E, and it would cancel it out, except I don't really want to have 1 over Y. I want to just have Y. So since that's going to be my strategy, I'm going to change this to where this is just a Y before I do that. Now, how could we possibly do that? So my idea is to multiply by -1 again. So if I multiply by -1, then that means, once again, that this could jump inside as an exponent. And remember that a negative exponent just means to multiply by the reciprocal. The reciprocal of 1 over Y is Y. So this means that this would just be the natural log of Y. But now this side has a has a negative on it. So this is negative W of -k. Whew, okay, so we're here. Now, remember, I can cancel out the natural log by doing e to that power, right? That cancels out. So let's go ahead and do that. So e to this power, but wait, if I change one side of an equation, I have to change the other side the same way. So this is now this. This side cancels out to y, and I now have it equal to e to the power of negative w of -k. And I did it. We have y by itself. It seemed like maybe an impossible task when we started with this simple problem that turned complicated, but we got here. We have y by itself. But I still don't like that we started out with y's and x's, but right now I have k's. So let's now at this point remember that k was actually just representing the natural log of x divided by x. So we can now take that and remember that, right? K is just the natural log of x over x. Also, I prefer to write things as y equals, so I'm just going to kind of switch sides here. So we have y equals the e to the power of negative w of -k, but k was the natural log of x over x. Okay. So we did it. We're back to expressing everything in terms of the original variables, x and y. The only thing I really don't think is ideal here is just that we have this weird like w function. Remember, we know what the w function is though. So if we need to compute things, we can compute these and then just kind of switch our inputs and outputs so we can kind of deal with it here. So in other words, we can get values for our W function out of that. So what are we going to do? So I would like to now think a little bit about the graph, because we've accomplished one of our goals. The first goal that kind of stumped the roomful of math teachers when we were posing this problem was, how would we actually solve this for y? And I have managed to do that using, this is all like Algebra 2 level stuff, although using it in a way that is maybe beyond what most Algebra 2 level students would do. And I did have to use the Lambert W function, but I defined what that is. So technically, you could just explore this and then just create this function for yourself. I need to do the inverse of this. So I did, and now I can just get its values by doing the inverse of these values, inputs and output swap. Okay, so technically, we've been Algebra 2 level at this point. Cool. Very, very technically. All right. So what are we going to do now? I want to explore the graph of this thing. So when you graph the original x to the y equals y to the x, it looks like this, which is kind of interesting. And I would like to explain a couple of things about this graph now, because this is one of the other things that the roomful of math teachers couldn't figure out in the few minutes that we had to talk about it before our meeting ended, at least. Anyway, so it seems like as the x values get really big, the y values seem to almost turn into a flat line at 1. But do they? If I go far enough, would this ever go below 1? Or is this what is called an asymptote? Is this going to get infinitely close to 1 without ever actually going below the number 1? Or would it eventually get down infinitely close to 0 and it's just growing extremely slowly? So now that we've actually solved for y equals something, I think we could now explore this idea. Now, this next idea is maybe beyond the Algebra 2 level, although some Algebra 2 classes at least touch on the idea of a limit. Limit is maybe technically a calculus idea, but it's one of the basic ideas of calculus. Especially the thought process behind it is pretty simple. We basically are just going to say, what if I plugged in an absolutely gigantic input? Would it be getting close to 1, or would it be doing something else? This is the idea of a limit. As the inputs get really close to infinity, what would be happening to the outputs? So I want to look at what is the limit of this function as our input variable x gets infinitely close to being infinity. Now, I'm not going to get into the formal definition of a limit or any of that for the purposes of this video. So how are we going to do this? Well, one of the ways to think about a limit is, what if I just plug this number in for x? Now, infinity is not technically a number, but you could just kind of imagine it as representing a super big input. So what if I basically had the natural log of infinity here, and then divided it by infinity? Now, you can't actually do that, so we should just think of these as really big numbers. Now, unfortunately, I was hoping this wouldn't get into any more calculus ideas, but when I think about this, just this inside bit, right? Let's take this inside stuff, this stuff right here. Let's explore that kind of on its own. I guess I lost track of one of the parentheses, but we'll just add that back in there. So let's think about this. The negative natural log of infinity. So how about I just think about the natural log of infinity? What does that mean? Remember, the natural log of infinity would essentially be saying, remember the base here is e, so I'm saying e to what power is infinity? Well, so to get e to a power to be infinitely large, I would basically use an infinitely large value. So what we get here is essentially the natural log of infinity is basically infinity, and I'm dividing it by infinity, although it's negative. So the problem with infinity divided by infinity is I can't really tell if that's getting big or small or anything. So this is what we call an indeterminate limit. Oh no. So this is where, again, I'm going to have to reach into a little bit of calculus. So at this point in the video, you could stop here, but there is an idea for taking limits. That is called L'Hopital's rule. If you get an indeterminate limit like we're getting here, then there is a trick. The trick is I could take the derivative of the top function and the bottom function, and then I could evaluate the limits of each of them separately, and then we could look at those limits divided, and it will be the same thing. I'm not going to make this video longer by proving L'Hopital's rule. So just take my word for it. If you've taken Calculus 1, you have experienced L'Hopital's rule. Anyway, so at this point, the video is becoming a little bit more advanced, but let's go ahead and deal with this. So we have negative ln x over x, and we want to take the derivative of the top and the derivative of the bottom. The good news is that the derivative of x is just 1, so that's going to completely simplify out. Now, the derivative of the natural log of x is one of the derivatives that you're supposed to just kind of memorize when you're doing calculus. You could Google search it. It's just 1 over x. The derivative of the natural log of x is 1 over x. And again, while we could make a whole other video proving that, we'll just at this point say that if you're watching this part of the video, you're somewhat familiar with calculus. And so this is going to become 1 over x, and then the negative sign just kind of hangs out there as well. This becomes a 1, and we're here. So now I want to evaluate the limit of this as x goes to infinity. And this would, the divide by 1 just doesn't really matter. So we're really just asking ourselves, what would happen if I divided 1 by infinity? What would it be infinitely close to? And remember, this isn't really infinity. It's like infinitely close to infinity. We're getting super, super big. So 1 divided by a super big number is 0, and negative 0 is just 0. So the limit of negative ln x over x does end up being 0. Okay, now, we weren't actually doing just that. What we were actually looking at was the limit of this whole thing. But what we're essentially saying is that this inside bit is 0. Okay, now this is why I needed my Lambda W function inputs and outputs, because notice that what this means is I need to evaluate W of 0. So I need to input 0 into my W function. So somewhere over here we had it, and when I input 0, it outputs a 0. So that's really nice, because that means that this is just e to negative 0. Okay, negative 0 is just 0, and any number to the power of 0 is just 1. So that means that as x gets infinitely large, this gets infinitely close to 0, which does explain why this is indeed an asymptote at 1. Now, why would there also be an asymptote vertically at when x is 1? Well, this is pretty easy to explain because this whole graph very obviously has symmetry. It's reflection symmetry over the line y equals x. Because notice that if I replace x with y and I replace y with x, we end up with the same function again, which means x's and y's are reversible here. So if you have a asymptote at y equals 1, you will also have an asymptote at x equals 1. So we've done a lot of things here. I've explained why the asymptote is here. I've explained why there's an asymptote here. Maybe we should at least touch on why you would get the point EE at that value. So we could maybe do that real quick and then call it a video. So why are we getting the point EE? Well, let's go back to our function that we're working with here, right? So we have this function. Why would I get E out if I input E in to this? How about we explore that before we go? So let's take this function and find some space to work with it. So what happens when I input E into this function? So I think we can actually answer that. So I would get E to the power of negative W of negative ln, that's an ln, that's not written very well. I guess I'll write it better. Negative ln E over E. Okay, now this is not too bad to evaluate actually, because the natural log of E is 1. Why is it 1? Because remember what the natural log of e means is the base here is e. So I'm saying what exponent would I use on e to get e? Well, e to the power of 1 is e, which means the natural log of e is 1. So this would simplify to e to the power of negative w of negative 1 over e. So what is w of negative 1 over e? Meaning, what do I get out if I input negative 1 over e into the w function? And you know what's really cool? That's one of the answers we already have. If I input negative 1 over e into the w function, it outputs a negative 1. So let's go ahead and do that. So I input this, and the w function outputs a negative 1. So e negative negative 1. And negative negative 1 is just 1, so this is indeed just e. So if you input e into our function, it also outputs e, and that is at least a little bit of intuition into why this is indeed the point EE, although I guess we didn't exactly explain why this curve hits at that point, and it intersects the line of trivial solutions where x and y are the same. That's the line y equals x, but I think this has been enough math for today. And I have no idea if you guys will enjoy the video. I hope all of you have an excellent day.